Not really. The 2/3 goes down to both sides of the numerator and the denominator.
Okay, so just for those who are struggling through the algebra, I thought I'd walk through part B. If you're fine with part B, then you can ignore me for a few minutes. So the idea with part B was that the off-axis magnetic field, you want to find where it is that it's 1/8 of the magnetic field at the center. And so I took that relationship that they want us to find and set the off-axis equation equal to 1/8 times the center equation, and what we're looking for then would be x. So a whole bunch of things are going to cancel, which is my favorite part. Okay, so those are everything that's the same on both sides. And then I have a squared over x squared plus a squared to the 3/2 is, what do I have left? 1 over 8a? Okay. So I'm going to cross multiply this. I think I might have done it differently on my notes, but I feel like cross multiplying for some reason. So that's going to become 8a cubed times x squared plus a squared to the 3/2. Okay, so the 3/2, what literally that means is this parentheses term is taken to the power of 3, and it's also square rooted. So if I want to get rid of the square root part, if you ever want to get rid of a square root, then you square both sides, right? So if I wanted to get rid of this part, then I'd have to square both sides. And so now we have to remember our algebra rules. When you've got 3 cubed, or something cubed and then something squared, do these things multiply or do they add? And I have to check my notes because I don't remember.
Add.
They add? I'll take your... Since I did it differently on my notes.
Because you can even skip, you can even jump a step rather than.
Oh, they do multiply.
Take it to the 2/3 power. You just want to take it to the inverse, because then they multiply together and become 1.
Become exponential decay.
Okay, so maybe a better way to do it. But I think it is multiplied. So we can do it this way, and then if we want to go at this step and do it a different way, we can. There's multiple ways to go about reducing from this point. So if we do it this way, it would be 8a to the 6th, and then this side would be x squared plus a squared to the 3rd.
You have to square your feet to the.
Oh, thank you. 8 squared. 8 squared a to the 6th. 8 squared is 64. Okay, thanks. Now we have to get rid of the cube, and to do that we have to take a cube root. So 64 to the cube root of 64. We know it's the square root would get us back to 8, and then what's the square root of 8? Probably don't remember. We could just call it the square root of 8, right? But once you see the square root of 8, then you remember how to reduce it, right? What can you reduce the square root of 8 down to?
It's just 4. The cube root is 64.
Oh, wait. So it would be 4?
4 times 4 is 16. 16 times 4 is 64.
Got it. So it doesn't work quite the way I was thinking. So maybe we just need to rely on our math skills that I don't remember. So, okay, 4. And then when we had 3 times 2, and then if we now divide by 3, then this goes back to a squared. And that leaves us with x squared plus a squared on the right-hand side. We're trying to get x, so we'll get x squared by itself. And then now we have 4a squared minus a squared is what? 3a squared. So now you have x equals the square root of 3a squared. Did I do it right? Is that what you guys got? Okay, my algebra works. So you could write that as the square root of 3 times a. And you guys found a in part 1. So that's a pretty easy calculation then from that point. And then just one last thing I wrote on my solution back there anytime you take the square root of something, your answer can actually be plus or minus, which makes sense because it wouldn't matter whether you're above or below the coil, the B field would be the same at that distance. So it would just have a different direction. Okay, so any other questions about this problem? Did you guys want to go back to this step and do it a different way, or are you okay with this?
I guessed and checked until I got the right answer, and it ended up being right.
Okay.
The only reason I say the 2/3 is because then it makes it less likely that you'll make a computation error in that step. Knowing that two exponents on either side of parentheses are going to multiply together, and you want to get it down to 1. You can just take it to the power of the inverse of that 3/2 power. You have 3/2 power. If you just take the whole thing to 2/3 power.
So wait, a cubed is x squared plus a squared to the 3/2. And so you're saying take the whole thing
to the 2/3 power.
Okay.
Then when you multiply 2/3 by 3/2, you get 1.
So this just becomes x squared plus a squared. And this side,
Threes cancel.
so you have a squared.
The cubed root of 8 is 2 squared is 4.
Okay. So you'll get
And then
the,
you subtract a squared and you get 3a squared. It just gives subtracts.
yeah, it does. Yeah, okay. So it's always nice to see multiple points of view, since we all think about these problems slightly differently. Any other questions about this problem? So it's 11:24 now. Do you guys want to power on till lunch, or you want to take a 5-minute break? Nobody wants to take a break right now? Okay, we'll keep rolling. Okay, so the next little bit is leading to something applied. So we don't really need to write this down per se unless you're just really into new physics equations. We're not going to use this equation outside of what I'll show you in a minute. But this is one of Maxwell's equations. So at the beginning of the term when I said we would learn 4 Maxwell's equations and all of electromagnetism can be described with those 4 equations, well, Ampere's law is one of the 4. So this has a lot of broad applications. We just don't necessarily get into it at this level. So Ampere's law, this is used to find the magnetic field due to a cluster of current-carrying wires. So what we're going to use this for when we kind of develop it is to find the magnetic field due to a solenoid. But let's kind of just talk generally about Ampere's law, this equation. The circle on the integral symbol, did we see that already with Gauss's law? Okay, so we know that that was for a closed surface for Gauss's law, and for Ampere's law, it's just a closed loop. So we're integrating around a closed loop. And an Amperian loop is just like a Gaussian surface. It's completely arbitrary. We pick it. So if you've got a whole bunch of wires, and these wires are sticking in or out of the page, or they're sticking out of the page and the current's either going in or out. So let's say you had like 10, but you only wanted to find the magnetic field due to these 3, then those are the 3 that you encircle with your Amperian loop. And this will tell you, using this rule, only the B field due to the currents that are enclosed by that loop. So it's a lot like Gauss's law. So if you've got, to figure out I enclosed, if you've got 2 wires coming out of the page and 1 wire going into the page, they kind of work against each other. So the net current enclosed would be I1 minus I2 plus I3. So the ones coming out of the page are positive, and the one going into the page is negative. So, okay. So we figured out what I enclosed is, and then we've got a dot product in here. So a dot product for B dot ds would be B ds cosine theta, but of course we usually put the integration symbol at the end, so I put ds at the end. I plugged in I enclosed, and then you could solve this through. You could integrate through and solve for the magnetic field, which we don't really need to do. That's not really what we're concerned with at this point. A couple things is that the Amperian loop, we always choose a loop where the direction of integration is counterclockwise. And that way, if you do it that way, the currents coming out will always be positive, and the currents going in are always negative. Okay, so let's talk about the solenoid. A solenoid, as I was talking about earlier, would be a long cylinder of tightly wrapped coils. And it's defined as a solenoid if the radius is much, much less than the length. So this is a cross-section of a solenoid. So imagine a cylinder of tightly wrapped wires that you took a saw to and you just sawed it in half. So you're going to see where the current is coming out of all those wires would be on the bottom, and then where the current goes into the board would be all the wires on top. And we want to find the magnetic field inside a solenoid. So we're going to use Ampere's law to do it. And so my Amperian loop is this square made by the points A, B, C, D, and then back to A. And so again, we choose this counterclockwise. Did I say counterclockwise? I think I said clockwise. But the currents are going into the board. I don't know why they did it this way. They decided to integrate clockwise, and the currents are going into the board, and they made them positive this time. So blame the book for being confusing. Yeah, Nolan?
First of all, what exactly is a solenoid? What's the difference between a solenoid and a coil?
A solenoid is a device that creates a magnetic field. And we learned with the coil, and this is also true with the solenoid, that the more wires you have connected, it just magnifies your magnetic field.
Okay, so the solenoid could be a really big coil?
To be defined as a solenoid, the radius has to be much narrower than the length, and whatever, that's a very ambiguous definition. But with the solenoid, your wires can't be overlapping the way that these they're overlapping all over the place. We assume that this is just a coil, using all those equations, those 4 equations that we wrote down earlier, these 4 equations. So to be a solenoid, you'd have to really carefully wrap this around a cylinder so that you only have one coil, nothing laying on top of each coil. And then they're evenly spaced, and then things will work happily in that case.
Are the wires making contact with each other?
They're coated, just like most wires that we use are coated.
Oh, okay.
So they're not...
There's no conductivity going on in between them?
Yeah.
Oh, okay.
And they all are connected to the same supply, so every wire is having the same current running through it. And solenoids are used, like an MRI machine, I think uses a giant solenoid to create a magnetic field that's really big on your body. So it's used to create magnetic fields. That's the point of a solenoid. And Kelsey mentioned this application, an inductor. So an inductor is a device that you can put into a circuit, and it's basically a solenoid device. And so inductors have a lot of applications. Transformers are made with inductors. So solenoids come up a lot in everyday life. Okay, so to do the integration around this loop, we split it up into an integral for each step of the loop. So we broke this up into an integral from A to B, B to C, C to D, and then D back to A. And then writing out the dot product, we're writing the angle here between the magnetic field direction and the direction of travel around that loop. So from A to B, the direction of travel is to the left, and the magnetic field is to the left. So that's where this cosine of 0 comes from, the angle between the direction, ds, and the magnetic field, B. Quick comment about how we know the B field would be to the left. If you look at one of those wires, the current is going, let's see, out of the board and then into the board. You can use your simplified right-hand rule and curl your thumb in the direction of the B field, in the direction of the current, and then your fingers are inside the coil pointing in the direction of the B field. So I see my fingers are pointing to the left. So that's how we figured out the direction of the B field is to the left. Okay, so we've got B cosine of 0 ds, and then from B to C along this section of wire, when we're inside here, our ds direction is up and our B field is to the left, so that's a 90-degree angle. But of course, once we actually get out of here, in an ideal solenoid, there's no B field outside. So there's actually, B would be 0 right here for this stretch. And then from C to D, B is equal to 0. So C to D, I just crossed out the B term. It goes to 0. And then A to D, again, the angle is 90 degrees. So what's cosine of 0 degrees? 1. What's cosine of 90? And then B was 0. And then we have cosine of 90, which is also 0. And so all that's left from your integration was the path from A to B. And then the next three paths all equal 0. The B field was constant along our path from A to B, so we can pull that out. And then if you just integrate ds, that's just going to give you s, which is a length. And so this picture shows us that the length is called L, and so that's why I replaced it with L down here in the equation. So that's the result of the left-hand side of Ampere's law. The integral of B dot ds gave us B times L, and the right side of Ampere's law was mu naught times I enclosed. So that's a pretty simplified equation for a solenoid. So let's look at that a little bit. Let's say for our solenoid, we let little n be the number of turns per unit length. Sometimes they're called loops. Sometimes they're called coils. So that's terminology there. If we let the total number of turns be big N, then big N would equal little n times L. Does everyone understand that? If little n is the number of turns per unit length, then big N would be little n times L. Okay. Then the enclosed current would be the sum of all the currents for all the wires. So for one individual wire, the current was I. So I enclosed would just be N times I, big N times I. And then you could make a substitution here for big N. We just said that was little n times L. So what we had up here was BL equals mu naught times I enclosed. So if you plug in for I enclosed little n L times I, we would see the L's cancel on both sides, and we get this result down here. The magnetic field due to a solenoid is mu naught I times little n. That would be useful if you knew the turns per unit length. And then if you know the actual total number of turns and the length, then you could use this version of the same equation. Oops. So if you've got your solenoid and you know the length of the solenoid and you know the number of turns or coils or loops, then you can find the B field inside would be mu naught I n over L, or mu naught I times little n. So when we do lab, we are not making a solenoid. I want to repeat, we're not making a solenoid. We are creating a coil that is one dimension thick, so we're not overlapping our coils, but we're just wrapping it 10 times. So the width of the coils is very small compared to the radius. So that doesn't qualify as a solenoid. And so when we're in lab, we're going to use the equation that we learned here, number 4. If you do use a solenoid equation, in your analysis, you're going to lose points, because I'm telling you right now that you did not make a solenoid in lab. All right. So in the real world, you know, this is like a good equation, and it works very well. For the most part, the B field outside a solenoid is very, very small compared to inside a solenoid. But of course, in the real world, there is going to be some B field that gets out. So as engineers, you guys need to be aware of this is an approximation, and in the real world, there's going to be some fringe effect that gets that magnetic field out a little bit. Any other questions about solenoids? We've got one more topic, and that's a toroid. That's like a solenoid that you just turn into a donut. So this is a cross-section of a toroid, and you can see that it can be a little confusing because it looks like there's an inner and an outer radius. But what they're finding is the radius that, what they're calling R in this equation, is the radius that's smack dab between the inner and outer coils. So that's the R that you need to plug into your equation up here.
So if you were to open it back up to form a solenoid, the distance would be from the center of the donut to the center of the tube.
Yeah, from the center of the donut to the center of the tube that you've curled. Yeah. So how many people have ever opened up their computer and seen the motherboard? You've seen the little solenoid sitting on your motherboard? It looks a lot like this. Yeah. Solenoid, toroid, I should say. So we've seen toroids in practice, so that's the only application I know. I'm sure there's other applications.
A lot of transformers are just like that.
Oh, okay. Transformers,
More circular than
like a solenoid. Okay.
the
All right.
What are the path 1, 2, and 3? Are those the currents or?
Those are paths of integration. So this came from a picture where they prove that the B field is approximately 0 inside and approximately 0 outside, and then you find the B field to actually have a value only inside the coil itself. So that was just a remnant from a problem that they did with this picture. Yeah, Chris?
So if the B field, so if you have a toroid, right, that's enclosed, and you're creating a magnetic field within the toroid, but it's 0 within the donut, and approximately 0 within the donut, and approximately 0 outside of the donut, what's the application? Is that a larger question?
No, it's a good question, and it just kind of gives me pause. I'd have to read more about toroids, so like how they're actually working. I know we'll talk about inductors next week. So a transformer is an inductor and an inductor that are nearby each other, and they're not actually connected to the same circuit. And the way inductors can work is they can actually create current in that other loop with their magnetic field, and so you can charge a circuit that's unconnected with those magnetic fields. So, you know, if the transformer, like Kelsey said, uses a toroid, then there must be some way for that magnetic field to emanate outside the toroid. So, I mean, I guess that's getting a little beyond my knowledge. So I'd have to get back to you on that.
Yeah, no problem.
It's a good question, yeah. Yeah, your book probably would tell you the answer to that, because the book has a lot
In
of,
a long-winded, complicated, and not easy to understand way.
yes. They like to explain a lot of very random topics in painstaking detail. Okay, so the last two problems in your worksheet, one's a solenoid problem and one's a toroid problem. So let's see. Let me see if there's anything tricky about these. No to the solenoid, not tricky at all. Yeah, okay, so the toroid problem I think could be a little tricky because they give you superfluous information, and I think they do that to kind of keep you on your toes. So problem 2850, the toroid problem, they tell you the inner and outer radius first thing first. We just said before that that's not the R that we're using in our equation. And then it gives you the current, and it gives you the B field, and it gives you, and then it says it gives you the B field at points within the coil 14 centimeters from its center. So they wait till the very end to give you the R that you're actually going to use in the problem. So those first two radii are just red herrings to throw you for a loop. So if you want to work on those, you can, and that's really all we have left of the lecture. So when you're done with that, I can show them on the board if you want, or if you're done, you can go to lunch, and we will be back at, how about 12:30? Does that work? Yeah.
Yeah, I think, pretty sure we're supposed to use that, just.